Now, what this says is that under resting membrane potential, in this next slide, it's saying that the concentration of potassium is high inside the cell, low outside the cell. That's what we just said. At the same time, sodium is the opposite. Sodium is high outside the cell and low inside the cell. Okay, so this again is looking at the combination of electrical forces and concentration forces. Concentration of potassium is high. Concentration of potassium is high. That means that normally the efflux of potassium is outside of the cell. If you lose a lot of potassium out of the cell, that will make the inside of the cell even more negative. That would be hyperpolarization. If the interior of the cell gets more negative, that would be hyperpolarization. The pump, that is the sodium-potassium ATPase pump, the pump repolarizes the cell. Now this can be difficult. Depolarize, repolarize, hyperpolarize has my brain polarized. Depolarization is the rapid flux of sodium into the cell. Depolarization is the rapid flux of sodium into the cell. That's a fast. Repolarization is based on the pump. Hyperpolarization would be potassiums leaving the cell, leaving the cell, leaving the cell, making it more negative. Now, the major ion that controls the sensitivity of the cell's resting membrane potential is potassium. That's why potassium is so dangerous to your heart. If your potassium level goes low, your cell gets pissed off and you have an arrhythmia. If your potassium level in the extracellular fluid is high, you get an arrhythmia. When they're doing executions in good old places like Texas, you watching this in Texas? How you stop the heart is you give them a squirt of potassium. It stops the heart. I'm not saying you should do that, but that's what you could do to stop the heart. Now, when you increase potassium conductance, that is the flux out of the cell, flux, efflux, flowing away. When you take the potassium, which is a positive charge, out of the cell, that leaves the inside of the cell more negative because I took the positive forces out of the cell. That's called hyperpolarization. Hyperpolarization means it ends up being more negative than the -70 that it should be. Now, when you have increased extracellular ions, the concentration gradient, when the potassium level goes up outside the cell, when the potassium level goes up outside the cell, what ends up happening is that concentration gradient is changed. Normally, potassium is very high in the cell and low outside. Concentration gradient takes it out. But when I raise the potassium level outside the cell, it prevents the potassium from leaving. Normally, potassium is very high in the cell, low outside the cell. Big gradient comes out. When I raise the extracellular potassium, I decrease the gradient and potassium doesn't leave. That's what the second line means. Increased extracellular reduces the flow out of potassium. And in fact, if you were to raise the potassium levels up outside the cell a lot, you could create an influx of potassium, and that ends up depolarizing the cell. Depolarizing the cell, does that mean that the intracellular environment, depolarization, does that mean the cell becomes more negative or more positive? Depolarization means that the cell becomes more positive. If a person has rhabdomyolysis, hemolysis, tumor lysis, what happens to potassium levels in the blood? It goes up. If the potassium levels suddenly go up, it can create an influx of potassium and depolarize the cell, and that's why you die of an arrhythmia. A person comes after they've had a seizure, after being run over by a truck carrying pravastatin, simvastatin, fluvastatin, and atorvastatin. How do they die? What is the most urgent step? How do they die? They die of hyperkalemia. What is the most urgent step? An EKG. Because when the potassium level rises, the potassium can go into the cell and abnormally depolarize it. And that kills you. Now, if the potassium levels are down outside the cell, you'll have more flux out. If the potassium levels are down outside the cell, more potassium will come out. And if more potassium comes out, the interior of the cell becomes more negative. If the interior of the cell becomes more negative, it hyperpolarizes the cell. Potassium is the main thing that affects a membrane potential. Now, sodium. The thing about sodium is higher outside the cell. Sodium is higher in the plasma. It's lower inside the cell. Okay. Sodium is not as important in terms of the resting membrane potential because the conductance is generally zero. Now, if you have an increase in membrane conductance, the sodium ions rush into the cell. When the sodium, which is positive, rushes into the cell becomes more positive. And that sudden positivity inside the cell is depolarization. The cell is normally negative. The cell is normally negative. If sodium rushes into it, it depolarizes. Now, even though the sudden rapid entry of sodium into a cell depolarizes it, the resting membrane potential is not based on sodium because the sodium channels are normally pretty much closed. The resting membrane potential is based on potassium. This is why the extracellular sodium doesn't change the membrane potential. This is why you don't die of arrhythmias from sodium disorders. Sodium disorders don't cause arrhythmias. High potassium, peak T waves in the EKG. Low potassium, U waves on the EKG. High and low potassium changes resting membrane potential a lot. You die of an arrhythmia. High and low sodium, no EKG abnormalities. High and low sodium, no conductance disturbance. High and low potassium, conduction disturbance. Sodium gives CNS problems, but hyperkalemic conditions give cardiac problems. And hypokalemic conditions give cardiac problems. Kalemic cardiac. Sodium is CNS, but you don't change resting membrane potential with conductive tissue, electrical conductive tissue, not changed with sodium. It's changed with potassium. Next slide. Resting membrane potential. Here we go again. The interior of the cell is negative. When potassium comes out, the normal efflux, the interior of the cell becomes more negative. If you suddenly raise potassium outside the cell, you can get an influx of potassium, conduction disturbance. If you suddenly drop potassium outside the cell, you make the efflux greater. Again, that changes resting membrane potential. Kalemic problems cause cardiac conduction problems. Now, this is a very different word, pump. Pump means active. Pump means energy. Pump means active. Pump means energy. And the pump pumps potassium into the cell. Passive diffusion goes according to a concentration gradient and an electrical gradient. The pump is to overcome the electrical and concentration gradient. The pump is to overcome the electrical gradient. It's negative in the cell. There we go. Now, depolarization. Depolarization means that sodium, which is positive, goes into the cell. When the cell is normally negative at -70, -30, 0, +30, when the sodium goes in, the electrical potential changes to a positive state. That is depolarizing. Depolarizing means the cell becomes positive. Hyperpolarization is the other way. Hyperpolarization means it's getting more and more negative. That's hyperpolarization. Potassium leaving the cell makes it hyperpolarized. Sodium going into the cell makes it depolarized. The transmembrane difference, the potential, is the difference across that membrane. That's what we're talking about here, -70, -90. Now, this is a short chapter, but it's difficult. It's difficult because the word depolarize, repolarize, hyperpolarize all seem to have that phrase polarize in it. So what do we understand here? The inside of the cell is negative. That should keep potassium in. The concentration of potassium is high in the cell. That pushes potassium out. What is normally happening? Potassium is going out. Any sudden changes in potassium kill you through an arrhythmia. When the potassium level suddenly drops outside the cell, there's more efflux, the cell will hyperpolarize. When the potassium level suddenly goes up outside the cell, the potassiums can go in and you depolarize the cell. The bottom line is, the major effect upon transmembrane potentials is potassium. Potassium problems cause conduction defects and it causes arrhythmias. Sodium problems don't cause arrhythmias. The difficulty with this is to understand a combination of concentration changes and electrical forces. I recommend that you read this 17 times until you finally get it. The clinical questions will have to do with EKG abnormalities. The other way of saying it is this. When you get a potassium question, say EKG, and you'll probably get it right. Okay? Another way to look at this is, if we have a cell, and the interior of the cell has an electrical potential of one type, and outside the cell, you have a different level of potential, a property of the ion. Potassium will leave the cell in order to try and make these two equal. So, if you have the interior of the cell at -70, but as part of the Nernst equation, forces that are trying to bring things into equilibrium, this would show that sodium will not go in, because if sodium went in, it would end up making the interior of the cell more positive and the exterior of the cell would become more negative. So sodium going into the cell would not be good, would not bring it into equilibrium. Potassium coming out of the cell will make the outside of the cell more positive and the inside of the cell more negative and bring it into equilibrium. So the ions move in and out of the cell trying to bring the electrical potentials into equilibrium.